Okay, good morning. Let me summarize some of the discussion that we already had. And in order to do that, let me open the slides, okay, that are named controller design, okay. The first part of these slides are just the same slides you have in the previous say block of slides. Okay, I put here just for students in mechatronics to say not download also the other block of slide number 7. Okay, so here you have just something that we have discussed before. Okay, so let me summarize what we said. And the topic is to discuss what happened when you are no more in steady state. Okay, steady state means that all the variables are stable. Okay, there are no transients at all. Voltages and currents are exactly that we designed. So we are in our what is called DC operating point. Okay, the target output voltage is constant and nothing changes cycle by cycle. So you have what is called also a cyclostationary condition. Okay. For example, in cyclostationary condition, we derived the properties of the basic switching mode converter topologies. Okay, we derived the conversion ratio of the buck boost, and the choke converter. And then that situation, we derive the peak value, the root mean square value of the current, the electrical stress of components, etc., etc. Okay. Now we are moving to another kind of situation, that in which you have dynamic variation. So this is a situation that always happens in any circuits. Okay, something that perturbs the steady state situation. For example, because there are disturbances. Okay, and disturbances can come out from, I don't know, disturbance from the environment, the electromagnetic environment, something that changes the, I don't know, the load, or something that can change the input voltage. Okay, but the goal of any kind of voltage regulator is to maintain constant the output voltage. Okay, the output voltage V0 should be always the same, even if you are in presence of large amount of disturbances. Okay, or if you are in presence of large amount of disturbances, you have a variation, a dynamic situation, a transient, but then you have to recover almost immediately what is your target output voltage. Okay, and this can be done in, say, stability. You have you should not have any problems of instability. For example, that can happen when you have a variation of your output voltage due to some disturbances, and then you cannot regain your target output voltage, or maybe you can regain your output voltage but with a long oscillations, ringing, that can, say, induce several problems in your applications. Okay, so I can admit dynamic situation because disturbances always happens. Okay, but I have to recover the correct situation, the stable situation, without much oscillations and ringing and what is called instability. Okay, in order to do that, all kind of switch mode power converters always are designed in strictly conjunction with a controller. It is a circuit that is devoted to generate the correct set of control signals in order to, let's say, compensate the variation of the output quantity. Okay, when you have disturbances that induces variation of the output quantity, okay, this variation is sensed by the controller, and the controller provides a compensation, generate a different control signal, and the control signal is basically the duty cycle for our converter, in order to, let's say, recover this variation, and then you to recover the, say, cyclostationary condition. Okay, this is my goal now. So we see that there are several different kind of feedback controller. Okay, they are always closed feedback controller, so they sense the output voltage and then in some way generate a new set of control signal. Basically, I said there are the voltage mode control, which sends the output voltage generated in this cycle, and the current mode control, which sends another state variable, which is the inductor voltage, and together with the output voltage generates the current control signal. So in the following, we focus our attention on the voltage mode control and the current mode control. Feed forward is another kind of control that I already described, but this is all the advantages are included in the current mode controller. So let me describe, and this is, I have to share my whiteboard here. Let me describe the behavior of the system in this dynamic situation. Okay, I have the controller, sorry, I have the converter. Okay, this is my converter. And the converter can be described in terms of a generic block inside which you can have the buck, the boost, the buck boost, etc. Okay, its main output is the V0 voltage, and then you have the input voltage, then you can have the output current I0, and then you can have the duty cycle, which is your control quantity. Okay, so this is a switching converter. Switching. Okay, so as I said, we have to maintain VO stable when you have variation of these three quantities. Okay, these two quantities here can be regarded as disturbances. It means that they have to minimize. Okay, I want to minimize disturbances. I want to minimize the impact of the variation of these V in and I naught on the, say, output voltage V naught. So this is something that I want to minimize. Of course, this kind of variation always occurs because V in is the input voltage of the switching converter. Think about what happens when you have a rectifier, which is placed at the input of your converter. When you have a rectifier, okay, is a block which you have diodes. Then you have here a, say, sine wave. I'd like to have here a DC waveform, okay, and then you have a filter here, and then maybe you have the converter, the DC-DC converter here, DC to DC. This voltage is a DC, the voltage at the input is, say, something which is not something like this, okay, as a frequency which is 2 times that of the input main, but is not constant. So I want to minimize the variation of the output voltage when you have this variation, for example. Okay, so this can be considered as a disturbances. The same happens for I0. I0 means that there is a change in the load, and this always happens because the load is not fixed for, say, any time instant. The load at the output of your, say, converter, your DC to DC converter, can change. R is something that can change, so the output current change. But whatever is the resistance you can have here as a load for your converter, you want to have the same output voltage. So the variation of the current should be minimized. So I can regard the V in and not as a disturbance. To me, was effect has to be minimized, was effect on the output voltage. Then you have the duty cycle. The duty cycle is your control. Is the quantity that exactly defines the time interval in which the switch is on and when the switch is off. And so this is the control signal that set the duty cycle. And as you can see, as you learned in the previous lecture, the V0 voltage depends on the conversion ratio. So V naught over V in, for example, that depends on the duty cycle. So the duty cycle is the exact quantity that provides you, let's say, the current output voltage. So is the quantity that can be changed in order to compensate the variation of V naught due to the disturbances. Okay. How can we say represent the variation and the transient that we can have in our converter? I can represent this variation by this symbol. Okay, so when I have this symbol here, as I employed in the previous lectures for electronic students, this means that I just talking about varying components, so the AC components. Okay, this is the AC variation components. So in that case, I'm not talking about the steady state, so DC quantity always constant. I'm talking about something which is varying. And among all the variation, I just focus my attention on the small signal variation. So when I have something that varies over a DC quantity, and this variation is well small, well lower with respect to the DC component. Okay, so for example, the voltage V can change, but the voltage V can change. For example, look at this waveform here. Can change, can have a variation superimposed onto a constant value. Okay, there is a voltage V in which is an average value, and then you have a variation. This variation here is something that I can call, and typically V variation is well lower than the DC value. Okay, this always happens for the I naught and also for the duty cycle. So let me consider this kind of nomenclature, so I can add this hat here, just to say take into account the small signal variation of the quantities over a DC quantity, so operating point. Okay, so this converter here is a converter which has some problems in describing this kind of relationship, the relationship between the variation of the output voltage V naught due to the disturbances and due to the variation of the control, because it's a variable structure system. Remember that I mentioned about the fact that you have switches, you have diode, and these as time variant component. So there is the necessity to describe the variation in terms of small signal variation. And in order to do that, I have to consider a circuit which is linear and time invariant. Okay? But our circuit is non-linear and time variant. I don't know if exists this acronym, non-linear and time variant, but now we have this space. I have to pass from non-linear time variant to linear time invariant in order to have this description in terms of small signal variation. In the previous lecture for electronic students, we derived the model for the switching converter, which is exactly linear time invariant. Okay, and we passed across two different steps, from time invariant to time variant, and from non-linear to linear. Okay, we get the first results, so from from time invariant to time invariant by averaging the circuit, and then from non-linear to linear by, say, linearization of the circuit. Okay, so consider that now, for all of you, this switch converter can be described as a linear time invariant circuit. If you use a linear circuit, then you can apply, for example, all the circuital techniques that are, say, employed for linear circuit. For example, the Laplace. Okay, and in terms of Laplace, we can say that V naught Laplace variable S variation, so the small signal variation of the output voltage, can be described in terms of the, say, contribution of each of these sources. So we can apply Laplace because the circuit is linear time invariant. And then we can apply the superposition effect again because we get a linear time invariant circuit. And this superposition said that I can analyze the effect of the output voltage variation in terms of, first, the input voltage. And so we get the input voltage variation induces variation in the output voltage through a specific GV-in, which is a transfer function. It's the transfer function between the variation of the input voltage to the variation of the output voltage. Then applies the superposition problem. I can just focus my attention on one, say, problems at a time. One is the variation of V. The other one is the variation, for example, of the duty cycle. So I have the duty cycle that varies, and the variation of the duty cycle are linked to the variation of the output voltage by a transfer function which is called GVD. And then you have the variation of the output voltage that are due to the variation of the output current, okay? And that are indicated by this quantity, okay? There are three different quantities that are, say, GV-in, GVD, and zeta 0 that I can separate because I can apply superposition principle. I can use Laplace because we are a linear time invariant system, and then link the variation of disturbance in the duty cycle to the variation of the output. Okay. Zeta 0 is called the output impedance. Okay. Why there is a minus sign here? Because when you talk about the output impedance, this is something that already came out when we discussed the converter. When you have a, say, circuit like here, we have a source, and this is the Thevenin, and this is the zeta 0, these Thevenin equivalent circuits. And then you have here your load. Okay, you describe your converter by an equivalent circuit. Okay, this is V0. The current for deriving zeta 0 is assumed to be entering the output node. Okay, something like this. So of course, when I0 increases, the output voltage decreases. So there is this sign due to this fact here. Okay. Remember that in our case, in our description, the I0 is as this sign here, so it's entering the resistance R. So in that case, you can put here plus. So the plus or minus here is just a convention. So depending on which way you derive zeta 0 is not so important. GVD, which relates the variation of the control signal duty cycle to the variation of the output voltage, is called the control to output transfer function. And GV-in is called the line to output transfer function. So let me summarize here the result. We have GV-in over S, and GV-in is defined in this way. It's simply the ratio between the variation of the output voltage with respect to the variation of the input voltage. When you get 0, the variation of the duty cycle and the variation of the output current. So is V0 Laplace with V-in Laplace when you get duty cycle variation, which is the same of output current variation, 0. This is called the line to output transfer function. Okay. Remember that we derived this kind of relationship in steady state for any converters we examine in that situation, and we call this variation as the audio susceptibility. Okay, so this means that this line to output transfer function is just the extension of the DC quantity audio susceptibility to any kind of frequencies. Then we have GVD as a function of S, which is the variation of the output voltage over the variation of the duty cycle, when the variation of the input voltage and the variation of the output current is null. This is called the control to output transfer function. Remember that again, we derived this relationship between the variation of V0 with the variation of D at DC in steady state analysis. And then we call this as the gain. And then we have zeta naught as a function of S, variation of the output voltage with respect to the variation of the output current, when you have V in and duty cycle set to 0, and this is the output impedance. Okay, so we can describe in this way the behavior of the variation of our circuit. Okay, so let's start this discussion by looking at the voltage mode control. Then we move to the control mode controllers, okay, after we finish with the voltage mode. So let's start with the voltage mode. The voltage mode is a typical closed loop feedback system in which there is, let's say, in which we sense the output voltage and feed back these quantities to the controller, the voltage mode controller, in order to vary the duty cycle to get the same output voltage to be constant. Okay, let me show, say, a diagram block, for example, for the buck converter. This is just an example. You can have all other converter in place of the buck. You can have the buck boost, the boost, etc. So we have the load here. In diode, L, the switch, C0, R, and finally we have V0. Okay, we have to control V0 to be constant for any kind of perturbation, both, say, disturbances like the variation of V in, the variation of the output current I0, and also in terms of the useful quantities, which is the duty cycle. We can have, say, a feedback that can be represented in this way. We have to measure the output voltage. Okay, so in order to measure the output voltage, we have a sensor. Okay, and suppose that we can, say, make reasoning for linear time invariant model of our converter, so we can put Laplace description. This is the transfer function of my sensor. We can call it the sensor gain. Okay, so the output voltage is sensed. The sensor has a specific transfer function. It behaves differently in versus the frequency. Okay, typically in voltage mode, this sensor gain is just a, say, voltage divider made by resistance. Okay, but we can look later to these different parts. Okay, now just me describe the behavior in terms of blocks. Okay, schematics. Then you have a comparison. Okay, I compare here what it comes out from the sensor, so H V0 here, and I compare to a reference voltage. The reference voltage is exactly what I want to get at the output. Okay, say to me, this is my target. Okay, do whatever you want, but you have to get this output voltage. Okay, of course, if everything is, say, stable, there is no perturbances, etc., the output voltage V0 is that correct one. So it means that H V0 is equal to Vref. Okay, for if there are no, let's say, problems, HV naught is equal to Vref. Okay? This is my goal, to have these two quantities exactly the same. I get this comparison, and I get what is called an error signal. Okay, here you have an error signal. The error signal is the difference between the two. So ideally, the error signal should be 0 if there are no problems. Okay. Otherwise, you have a positive error signal. For example, a positive error signal means that your output voltage is less than the output voltage you want to get. If the error signal is negative, it means that your output voltage is higher than the output voltage you want to get at the output. So in order to compensate the variation of the output voltage with respect to the steady state condition, you need a block here which is called the compensator. The compensator is the specific circuit we have to design, okay, in order to make possible for the system to recover its stable situation when you have some disturbances, and at the same time to get this kind of action, in the way the system remains stable without too much oscillations, etc., over voltages, etc. Pay attention that when the voltage, the error voltage is 0, for example, when you have no problems, the output voltage is exactly what you want to get, etc. The output voltage, the error signal is null. This compensator, when the error signal is null, generate an output signal, okay, which is exactly the output signal that provides the correct duty cycle for maintaining the circuit, say, in steady state conditions. Okay, so it operates in this way. When the error signal is positive, it changes the cycle in order, for example, to, let's say, if it's this the error signal is positive, it means that you have V naught less than you want to get. So if VE is positive, you want to increase the duty cycle. If V naught is, the error signal is negative, it means that V naught is higher than the reference, and so this means that you have to reduce the duty cycle. Okay. The signal which is output by the compensator, and this can be the control signal, okay, is the input of the pulse width modulator. The pulse width modulator is the circuit that has a control voltage as its input, and on the basis of this control voltage generate the correct, say, duty cycle. Okay, we have the gate driver. The gate driver is the specific circuit that, let's say, establishes the correct voltage and current level for the switch to be turned off and on. Okay, and then you can control the switches. This is voltage mode feedback loop. Okay, the voltage, the output voltage is sensed, and then you have the sensor that has a specific transfer function. You have a comparison with the reference voltage with your target. You have a compensator, that is a circuit that compensates the variation of the error signal in order to get what you want at the output. The pulse modulation is a circuit that provides you the, let's say, the correct output quantity, duty cycle you want to obtain the output voltage. Okay, this is the closed loop description in terms of, say, schematic view. This is a schematic block. So let me redraw this circuit in terms of our transfer function. Okay, so remember that I have my converter, and the converter are some disturbances that are Vi in, I naught, so the small signal AC variation of these quantities. And so I have here a block that describes the variation, and this is GV in. Okay, and GV in is something that produce this variation. I naught through the output impedance generate another variation, And then you have the duty cycle. Okay, the duty cycle variation generated by the transfer function, the control to output transfer function, another variation. This contributes, this is with the plus, this is minus, this plus, according to our previous description, generates the output voltage variation. Okay, this is my schematic of the switch mode power converters. Okay, no more the buck. Now we can generalize this description. Okay, this is just a graphical representation of what I write here. Okay, superposition Laplace expression that give us the output voltage variation in terms of variation of disturbances and the control signal. Okay, then we have that the output voltage, and this is the control block, is sensed. So now I superimpose on this representation what I described here for the control field. So HS, then you have the comparison. This is H. Then I have here the comparison, which is plus and minus, and this is V reference. This is the error signal, VE. We are talking about variation, so we can put this hat on the variables. We have here the compensator. Let me describe the compensator with the transfer function, which is GCS. Okay, is the transfer function between the control voltage at the output with respect to the error voltage at the input. And then we have here the pulse width modulator. And the pulse width modulator has another transfer function, which is GWM. Okay, the variable which exits the pulse width modulator is the duty cycle. Okay, so we have this description, okay, which is the same as before, but now I put here the transfer function of each block. Okay, here is just a transfer function. I derive the transfer function, which is GC here, and I define a transfer function which is GPWM for the pulse width modulator. Okay. Okay, this is the converter. We have this closed loop description for voltage mode. Okay, so now we can define the output voltage VO in this closed loop system. Okay, and what are the variables that now are input to this system? The input variable of this system are the voltage Vin variable, the output variable current, and the reference voltage. So I can have here the same description as before, say in terms of superposition description, so the summation of three different terms. The first one is Vref, then we have another terms that is multiplied by Vin, and another one which is multiplied by I naught. Okay, now this is the closed loop description of how the output voltage varies with respect to the variation of the quantity that you are at the input here. Okay, so you can derive, but for example, just this Vref. Of course, in order to derive this quantity here, you have to set to 0 Vin and I naught. Okay, so you have to put 0 this one and also this one. Okay, so they are not taken into account. If you take this kind of description, you can follow my, say, on the graph what happens here. You have V naught here, and then you have V naught multiplied H, sorry, after the sensor. This is the sensor. Then you have the error, and the error is Vref minus V naught H. Okay, V control is GC that multiplies VREF minus V naught. And then you have the duty cycle, and duty cycle, let me write here, duty cycle is G pulse width modulation, GC multiplied VREF minus V naught. And then you have V naught, and V naught is equal to GVD multiplied GPWM multiplied GC multiplied VREF minus V naught. Okay, so you have that V naught S is equal to GPWM S, GC S, GVD S, VREF minus V naught. Okay, so I have V naught here and V naught here. I can have V naught D1 plus GPWM GC GVD, which is equal to VREF GPWM GC GVD. Okay, and so if we want to get V naught over VREF, this is simply given by this ratio GPWM GC GVD 1 plus I miss H here. There is H in V naught. Okay, I have to put H. So it means that I have H over here. So it is H, G, PWM, GC, GVD. Okay, so this is V naught over VREF when I put I naught equal to V into 0. In the same way, you can, say, derive all other expression. Okay, so let me show you this this quantity again. V naught over S is GC GVD G pulse width modulator 1 plus H GC GVD G pulse width modulator multiplied VREF, and then you can get the other quantity. The other quantities are much more simple because only depend on the block GV in for V in with the same denominator. And then you have, if you get minus, for example, here you can get zeta 0, 1 plus H, GC, GVD, G pulse width modulation, I naught. Okay, so this is what happens for our variation of the output voltage when you have the closed loop voltage mode. Okay, so you can define a variable which is the open loop gain. The open loop gain is exactly H S G G S G B T S G pulse width modulator S. So as you can see here, you have the denominator is 1 plus TDS. You have 1 plus TDS, 1 plus TDS. We can replace by this open loop gain. The numerator here is simply 1 over H multiplied the okay, so you can rewrite in this way. P naught is 1 over h t1 plus t ref plus g v in 1 plus t v in minus zeta 0 1 plus t v naught. Okay, so this is my description. Let me have a little discussion about this term, the H term. The H term is the gain of the sensor. The gain of the sensor is something that we discuss at the end. Okay, so for now, the gain of the sensor can be set to 1, for example. Okay, just to not to complicate too much. H 0 to 1 at the moment. We see that we need for this gain, so we have to add this gain. Okay, but just not to complicate too much. I want to describe instead this gain here, which is the transfer function of the pulse width modulator. Okay, the pulse width modulator is something that is here. Okay, is the block that is placed here and takes as an input the control voltage that exits from the compensator, and at the output it generates the correct duty cycle. Okay, so let me discuss the pulse width modulator transfer function. Transfer function, which is GPWM of S. In order to describe this transfer function, we have to understand in which way this pulse width modulator is made. Okay, so how it is constructed. The basic operational principle of this modulator is this one. We have a comparator. Okay, this comparator has an input which is connected to the control voltage, so the voltage that exits from the compensator block. And at the other input, it has a triangular waveform. Let's say V triangular. The output is called Q. Q is my unitary switching function. Okay, it's a function that ranges from 0 to 1, and its average value is the duty cycle. Let me show how it is operated. This is the triangular voltage. And the triangular voltage, for example, is like this. It's something that is generated locally, okay, by an oscillator. Has a peak value which is, I don't know, Vm, okay? The frequency of this triangular voltage is exactly Ts, so the switching period I need for my converter, okay? The control voltage is something that, for example, exiting from the compensator can have this value here. So if we want to analyze the output QP, I have to understand that the comparator, say, flips its output anytime the control voltage is, let's say, the same of the triangular voltage. Okay, so for example, here, 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 here. When anytime the triangular voltage is lower than the control voltage, the output is 0. So it's 0, for example, here, and is 0 here, and it is 0 here, because the triangular voltage is less than the control voltage. Anytime the control voltage is higher than the triangular voltage, the control voltage higher than the triangular voltage, then the output Q is 1. So this is the correct way to generate the so-called unitary switching function. Okay. As you can see here, you have a, say, pulsed wafer. Okay, but this is not the only possible rules. You can have, let's say, okay, sorry about that. I have made a mistake because when the control voltage is connected to the plus. Okay, so it means that when control voltage is higher than the triangular voltage, then Q is I. Okay, so it's the opposite. Of course. The control voltage here is higher than the triangular voltage, so Q is high. When control voltage is less than the triangular voltage, then Q is low, and this happens. Okay, but in any case, you have the flip of the output voltage exactly when you have control voltage which is equal to the triangular voltage. Now the Q function is higher here. Okay. Of course, if you can exchange the plus and minus signs here, you can get exactly the operation I previously showed. Okay. So this means that the unit switching function is high, for example, during this time interval that we can call T on. And so during this time interval, the switch is on. Okay, here the switch is on of the converter. In the time interval in which the unitary switching function is 0, the switch is off. Which is the average value of this quantity? The average value of Q is, let's say, 1 over Ts, the integral of Q t in the t. If you suppose that this is 0 and this is 1, so the output voltage are, let's say, from 0 to 1, okay, then this means that you have exactly T on over Ts. So this is the duty cycle. The average value is exactly the duty cycle. Okay, so the pulse width modulator exactly generates this unitary switching function, making the transistor on and off, and generating a duty cycle which is that needed for the output voltage to be constant. But remember that my goal is to derive my transfer function. Okay, so let me plot on a graph what happens to the duty cycle in terms of the control voltage. The control voltage can be from 0 to the peak value of the triangular voltage. Okay, Vm is this value here. So the control voltage, in order to have always a comparison with at the input terminals of the comparator, the control voltage should be, say, vary in the dynamic of the triangular wave. Okay, so from 0 to the peak value. From 0 to the peak value, what happens? If the control voltage is 0, so the control voltage is, let's say, here, so the control voltage is always less than the triangular voltage. So here in this case. Also less means that the Q function is always 0. And which is the duty cycle in this case? The duty cycle, of course, is 0. What happens when the control voltage is at the opposite side of the dynamic? So the control voltage now is here, is equal to the peak value of the triangular voltage, Vm. But in that case, the control voltage is always larger than the triangular voltage. You are here. And your unitary switching function is always 1. So that means that the duty cycle is always 1. And for the value that are in between, okay, there is a linear variation, of course. So this is what happens to your duty cycle. Depending on the value of the control voltage, you can get all the duty cycles from 0 to 1. Okay? This representation can be also described in terms of control voltage, okay, in this way. When the control voltage is 0, you get duty cycle 0. When the control voltage is Vm, the duty cycle is 1. Of course, this is not our transfer function. Remember that the transfer function is something that is described in terms of frequency. So, for example, in the Laplace form. Okay, we can always say consider that the duty cycle as a DC value, so the value that is the steady state value that makes possible to get the correct output voltage, plus some variation on it. The same happens for the control voltage. Control voltage has a DC value that makes possible to obtain this duty cycle here, plus a variation that I can express by this hat on that. Okay, so this is the DC component, and this is just the AC variation. Okay, in order to see what happens. So I can replace these two quantities in this expression here. So I can have that D plus D is equal to 1 over Vm V control plus V control, this way. And in order to, say, analyze what happened to, let's say, my transfer function, I have just to consider the variation. And the circuit for the variation means that I have to not consider the DC term here. And so you have that in terms of variation of duty cycle, you have this quantity. Just AC variation here. This is a linear, let's say, quantities that can be expressed in the Laplace form. And the Laplace form means that I have that V, the variation of the duty cycle in terms of the variation of the control, is 1 over Vm. Okay, and so this is also ds over V control S. Is this our, say, transfer function we are searching for? Look at the block over here. The transfer function is D hat over V control, so the ratio between the output and the input. And so this is exactly what we search for. Okay, so this is G paths with modulation. So the transfer function of the modulator is G P Wm in Laplace domain, which is 1 over Vm, is a constant. Depends on the peak value of the triangular waveform. Okay, so in this way we can, for example, write the open loop as, let me for just a moment to have Hs here, even we can use as 1 in further derivation. Okay, this is my open loop gain, in which I replaced the G pulse width modulation of the modulator by the peak value of the waveform in the modulator. Okay, so H will be considered just 1. We can derive in further, say, analysis. This here is the transfer function of the compensator. And this is exactly what we have to derive to design the controller. Okay, we have to design the compensator. Vm is a constant, depends on the, say, how it would be fabricated. The modulator is the peak value of the triangular waveform that we use for comparing the control voltage in the pulse width modulator. And then we have GVD. GVD is the control to output transfer function of the converter. So this is related to our converter. Okay. What we done in previous lecture is to derive this function here. Okay, now I summarize what we previously derived. Okay, so let me show to mechatronics students what we get in previous analysis. Okay, so compensator, this is to be derived, This can be done, this is a constant, and this is derived previous. So it is fundamental to understand what we derived. Okay, so look at the, and this also is something which is good for electronic students, that now we have something that summarize our previous result. So we analyze the three basic topologies, okay, the buck, the boost, the buck boost. What is important to understand that the buck is typically operated in continuous conduction mode, okay? Because if you operate with the same output voltage and currents, the buck in DCM, you have a large electrical set of components, and this is not convenient. So buck is typically operated in CCM. So which is the transfer function GVD, the control to output transfer function that I have to put here in this open loop gain for the buck CCM, and this is something that can be described in this way. We have some zeros, and we have poles. This that I'm writing here is the general expression. Okay, some of these terms disappears in depending on the converter we are looking at. Buck CCM, for example, has not this zero here. Okay, as you can see, this here has a minus here, so this is a right half plane zero. So the Buck CCM has not right half plane zero, has just a left hand plane zero, so this zero here, which depends on the ESR. The ESR is the, say, resistance which is in series to the output capacitance. Okay, when the reactance of the capacitance is the same as the reactance of the ESR, then we have here a short, and these come out with a zero here. Then we have two poles. There are complex conjugate poles. For the buck, the poles are, let's say, 1 over L C naught. And the omega ESR, the zero, is 1 over ESR C naught. The gain, GVD 0, so this gain here, for the buck CCM is simply Vin. The Q factor which is inserted here is something which is R C naught over L, if you want to derive. But what's important is that I can describe the buck, which has this generic expression, in terms of Bode plot. Let me draw the Bode plot for the magnitude of this transfer function. So this GVD, J omega in decibel, in frequency. These are, again, GVD 0 here. Then it has two complex conjugate poles that comes out from the denominator. And so from this point, then you have 2 poles, then you have minus 40 dB decayed here. And then you have somewhere here at 0, which is FESR. And so you have minus 20 dB decayed. Okay? This is the Bode plot of the magnitude of GVD for the back CCM. FP, as I said before, is 1 over 2 P L C naught. And FESR is 1 over 2 P ESR C naught. The gain is V. Okay, so this is for, say, mathematical description, can be, say, in terms of these expressions. You can see there is a 0 here and 2 complex conjugate pole here, but in terms of Bode plot, you can describe by this expression. Okay, so constant up to equal to V up to the complex conjugate pole. You have 2 poles, so from now we have 0 dB decayed. You can have a slope of minus 40 dB for decayed up to the 0 due to the SR. As you can see here, this pole depends on L and C naught, but this has been derived by steady state analysis, and they are fixed, so they are not changing during the operation. So these 2 poles here are fixed, not moving, so these always have the same frequency. The same happens for the 0, because C naught is something that you design for steady state analysis, as we learned in previous lecture. ESR is something that comes out as a parasitic of C naught, so this is fixed. Of course, V in is not fixed because V in can change. Okay, V in depends on your design. V in can change from a minimum and to a maximum. Okay, so this quantity here can change depending on the value of V. This happens for back CCM. It makes no sense to look what happens to the back CCM. Okay, for electronic students, remember that we derive this expression by looking at the method which is called PWM switch method. Okay, we derive this expression. Then we have, for example, the buck boost. The buck boost and the boost are typically operated in DCM, in discontinuous conduction mode. So we derive GVD for this continuous conduction mode. Okay. In this way, we have the same expression as before. So let me rewrite the expression of the control to output transfer function. Then we have 1 minus S omega zeta, 1 plus S omega ESR, and then we have again the S omega 0 square plus S Q omega 0 plus 1. Okay, the same expression as before because it's the general expression. Now we have that here we have the expression that you have that gives you the omega ESR, and this is ESR C naught, the same as before. Okay. Again, in DCM you have no 0 here, no right half plane 0, and you have no 2 poles here. Okay, you have just 1 pole. Okay? So we can modify the generic expression that you have before in this one, 1 plus S over omega P. So it's much more simple. It's GVD 1 plus S omega ESR divided 1 plus S omega P. And omega P for the buck boost is 2 divided R C naught. Okay, so my output control to output transfer function has just 1, 0, and 1 pole. 1 left-hand plane 0 and 1 pole. Okay, the back CCM has 1, 0, right, left-hand plane 0, and 2 complex conjugate pole. Okay. Let me plot the body plot. Let me plot the body plot. Let me draw the body plot here. G, B, D, J, omega, fetchable. You have the gain, G, B, D. Then you have here just 1 pole, which is 1 over P R C naught. Minus 20 dB decade, and you have the 0, which is always the same as before. U, P, C naught, ESR. The gain for the buck boost is given by V in multiplied R over 2LFS. We derived this expression in using the circuit averaging techniques. Okay, this is constant. This is the frequency. Okay, so we have just 1 pole, but this pole depends on the resistance. So this is a pole that moves depending on the operating condition. So this is a moving pole, and this 0 is fixed because it all depends on parameters that you have today design C naught and ESR. The gain here is moving because it's moving according to the resistance R and V, so it can change up and down. This is moving and the gain is moving. What happens, for example, the boost DCM? For the boost DCM, which is another important converter, let me show here. The boost DCM has the same gain, the same transfer function GVD of the buck boost, so just 1 pole and 1, 0, and a gain. Okay, the same description you have for the buck boost applies also for the boost DCM. Okay, of course the pole and the gain here are different from that of the buck boost DCM I previously shown, but you can use this expression to find out what happens. For example, M DCM is simply V naught over V in for the DCM operation of the boost. Okay, so you have to apply here the ratio V naught over V in, and you can get this expression. Okay, and this is the buck boost I previously showed here. It's much more simple, okay, because it's just described it in this way. These are the basic 3 topologies that we can apply. Okay, boost and buck boost operating in DCM, and buck operating in CCM. Okay. Why we cannot use the, for example, the boost or buck boost in CCM? Because now this quantity here that I always neglect because omega zeta is infinite in CCM for the buck, and in DCM for the buck boost. Now, when you operate the boost or buck boost in CCM, it appears. Okay, and so it has some drawbacks that we can see next time. Okay, something I already said for, say, to electronic students, but say we have, say, make evident this, say, contribution here in next lecture. Okay, so boost and buck boost DCM, because they have no right half plane 0, so this is not present, and buck in CCM to avoid large electrical stress of component when it is operated in DCM. And the transfer function was here. This is a result of my modelization technique that, if you want to look at, are described in the slide number 7. Okay, and this is the result. Okay, and this the result, it will be exploited in design they controlled. Okay, in this table again there are, say, summarize some of the results. Okay, for example, the fact that you have fixed poles for the buck CCM, moving poles for the boost discontinuous, exactly here. Okay, of course in this table here you have the result for all the possible operation of the buck boost and buck boost both in CCM and DCM. But what I'm saying you is that typically buck CCM, boost and buck boost DCM. So we find out that we have the gain, the loop gain, which is described in this way. Okay. And if you look at, let me share my white screen here. If you look at what is written here, somewhere here, okay, good, here. In this expression, okay, I have that the variation of the output voltage as a variation of the reference voltage is described in this way. The variation of the voltage V out in terms of the variation of V in is this, and the variation of the output voltage in terms of the output current is described in this way. It is instructive to, let's say, see what happens when, for example, the open loop gain is very large, okay? Because this is my goal, to get so let's have, for example, V naught over V in transfer function when Vref is null and when E naught is also null. This is G V in over 1 plus T. Okay, so there is a certain benefit when TS is, let's say, large in magnitude. If TS is very large, so is much larger than 1, of course, TS is say something that varies with frequency. But if we have this T well large for, let's say, all the frequency we are interested in, then it means that this is simply G V in over T, and this means that is, let's say, goes to 0. So having a large open loop gain means that our disturbance effect due to the variation of the input voltage to the variation of the output is minimized. And this is a very, a good quality, okay? If I'm able to design a compensator that has a very large T for a very large frequency bandwidth, then what happens is that I can reduce almost to 0 the influence of the variation of the input in the variation of the output voltage. And remember that the variation of the output voltage for me should be almost 0, okay? And so, what happens to the variation of the output voltage in terms of the variation of the input current? This is as a minus sign here. Suppose that Vref now is 0 and also V in is 0. This is zeta 0 over 1 plus T. If T is large, then also this term goes to 0. So this means that my closed loop output impedance is 0. So I'm able again to reduce disturbances to, let's say, almost a negligible effect. So, a conclusion, we can say that feedback having large T minimize the influence of disturbances to the output. And this, of course, is a good quality. Okay, so large T. What is the effect of a large T in my control to output function? Okay, the control to output function is, let's say, closed loop control to output function is this one, when variation of the input is null and variation of the output current is also null. This is 1 over h multiply t 1 plus t. Okay, this is exactly what we derived before. Let me check. Here, okay, is this contribution here, Vref, V naught over Vref. So if t is large, what does it mean? That if t is large, this contribution is the same of 1 over h, because if t is large, much larger than 1, this is something like 1 over h. So my output voltage variation only depends on the sensor gain, transfer function of the sensor. Okay, in the case we put h which is equal to 1, means that this control function is 1. Okay, so I can use the voltage Vref, okay, the variation of the voltage Vref, to directly control the variation of the output voltage, because this is the quantity that I can use to control the output. Okay, for example, this t open loop gain depends on the s variable, so depends on frequency. At DC, so at DC, it means that you can have that, let's say, V naught over Vref for DC quantity is more or less 1 over h. This is a variable of s, h0. Okay, so that means that, for example, at DC, the steady state quantity depends only on the DC value of this sensor gain. Okay, it happens if t0 is much larger than 1. Okay, so that means that my control action in steady state condition with no variation, okay, if the open loop gain is very large, much larger than 1 at DC, okay, the variation of the output voltage V naught in terms of variation of the Vref, so the DC variation V naught over Vref, depends only on the gain, the DC gain of the sensor gain. Okay. So let me summarize our result. I need a TS which should be very large. Okay. So that means that I have to consider quantities that can be large, both at DC and both for, let's say, a very large, say, frequency terms. Okay, so for sure, I have to say that if I want to plot t, Bode plot t j omega, okay, in terms of frequency, for sure I know that I have to start with a very large t here, okay, at DC. Very large t at DC, so for frequency 0. And then I know that I need a very large t for any other kind of frequency, because ds should be large for, say, other frequencies that are not 0. So I have to understand what happens for larger frequency. In order to understand what happens for larger frequency, we have to understand the concept of stability. Okay, look at this kind of, let's say, description just as a review of something that you already know. So just say something which is very fast in the description. What is the stability of a system, and in which way I can, let's say, measure the stability? Okay, typically the stability of the system is looking at the open loop gain. For example, this is the module of the magnitude of the open loop gain and the phase of the open loop gain here. in terms of frequency. At a certain point, there is a frequency in which the loop gain goes to 1 in magnitude. Okay, this is called the crossover frequency. You should look what happened at this crossover frequency. So the gain is decreasing, okay? And if at this frequency you have the phase, okay, of the T, which is 180 degrees, for example, the phase is here, then you are sure that your system is unstable. Because in that situation, it means that your output voltage is not subtracted to your, say, control comparator here, but comes out with a reverse in sign, and so you get here the plus sign. So in that situation, you have not a negative feedback loop, which is the loop in which you compare the reference and the output with the minus sign, but with a plus sign. Okay, for that specific frequency, in which the loop gain has a magnitude which is 1 and the phase is 180 degrees, you get a positive loop. And the positive loop is not something that can be useful, so it leads to instability. So you have to understand that you should get crossover frequency when the phase of your system is, let's say, less than 180 degrees. So, for example, you have to get a phase margin. Okay, so I think that there are the notions that you already know. And the phase margin is something that you have to choose looking at your, say, the system you are designing. Okay, the phase margin should be, say, something that can be larger than what typically is enough to have, say, 60 degree, 90 degree of phase margin in order to be sure that any kind of operation of the components does not lead to, let's say, reducing the phase margin up to the point in which Φm goes to 0. Okay, I have to be sure that whatever happens, Φm is always positive. And so in order to be sure that, I have to, say, design Φm quite large. 90 degree, say 60 degrees, should be enough, but 90 is better than 60, for example. If you have this condition, which you have phase margin, which is positive, so the difference between the phase at the crossover and minus 80 degrees is positive, and positive enough, then you have a stable system. So it means that a closed loop induce no variation of the output that are, say, including ringing or over voltages, etc. Compared to this situation, which at the crossover frequency, so the frequency at which the gain, open loop gain, is 1 in magnitude, now the phase is less than 180 degrees. That situation, the phase margin is negative and leads this system which is at that frequency is positive feedback. And so in that situation, you can get instability of your system, okay? So what you have to get is something that is related to, let's say, the phase margin. So the loop gain should be quite large, okay? Should be for sure large at DC, and then you should be large up to the crossover frequency in which you have, say, a phase margin which is larger than 60-90 degrees. Okay, this is the reason to the stability you can get these results. Now, why the right half plane in boost and buck boost CCM that I should are, say, something that can lead to stability? An answer to this question I already said to the electronic students when I talked about the derivation. Okay, another say answer is related to the phase margin. Compare these two different situations. You have this gain loop, open loop gain here, as this body plot, okay? And then you have, let's say, a pole, FP1, then you have a 0, another pole, and this is the crossover frequency. Okay, the first pole make this T loop gain to decrease from 0 to minus 20 degrees. Then you have a 0, and the 0 ideally rise up plus 20 dB decade. So since before we have minus 20 dB per decade, then you have 0, and then you have another pole that decreases minus 20 dB per decade. Okay, so pole, 0, another pole. In terms of phase, suppose that this 0 here is a good 0, so left and plane, okay? 1 plus S over omega z. So there is a plus sign before the s, is located in the left hand complex plane. The phase of this 0 here is a phase that starts from minus 19 degrees and so rise up to, let's say, for example, something that rise up in this way. So this phase difference is exactly 90 degrees. So you have a first phase derivation due to the pole, that is this one, from 0 to minus 19. Then you have the 0 that rise up the phases, okay? And then you goes up. Look at what happens at the crossover frequency. The crossover frequency, if you follow this variation of the phase, you get a phase which is minus 90. And so the phase margin, so the difference between the phase value and minus 180 degrees is 90 degrees. So the system is stable. Good. Suppose now that in place of the left hand plane 0, then you have, say, the right half plane 0. So a 0 which is located in the wrong side of the complex plane, the right half plane. So it is described as 1 minus s over omega zeta. Okay? This is the sign that you are in the wrong plane. In that situation, what about the magnitude? Nothing changes. The magnitude of the loop gain is the same as before, because in terms of magnitude, there is no difference between a left hand plane 0 and a right hand plane 0. The difference comes out in frequency, in phase. Because if you look at the phase of a right half plane 0 is the same phase variation of a pole. So it's something that changed from this way, from 0 to, let's say, minus 90. So it means that instead of having this boost in phase due to the left-hand plane 0, you have a decreasing of the phase because it acts like a pole. And so if you look at the crossover frequency now, then you have, let's say, minus 270. That if you compare to 180 degrees, this leads to a negative phase margin. So this system is not stable at all. Okay? So this is the reason, if you want, why I cannot use the boost and the buck boost in CCM. Because in that situation, you have a right half plane 0 that can lead, if you want, to instability of the system. Okay? So we can start Friday morning at 10 by this consideration. Okay? We just derived some consideration about the loop gain. And so we can, say, conclude this phase, and then we can start by designing the controller in voltage mode for our converters. Okay? If you have questions, I'm here. Friday afternoon at 2:30, there is the buck boost open loop laboratory. So book your seat in order to have the to carry out laboratory activities. Okay, questions, problems, issues, whatever, remarks? Okay. Of course, you can contact me by email, so no problem about that. See you